Okay, here's some new stuff. Okay, I lied. It's not entirely new. We're going to talk about friction, but we're going to look at it in a new way. It's a new equation for solving for friction. So before, all we had to do was calculate it using trig or using the balanced force model because it was equal to something else in the force diagram. Well, there is a new way that we're going to calculate it, and it's like this. Now, the Fn is normal force, we know what that is, but I want to talk about what this weird symbol is. It's pronounced mu, as in mu, and what it is called is the coefficient of friction. Okay? What is it? Okay? It is a couple of facts. It's a constant number. It has no units, because if you look at the equation here, if you solved it for mu, you would have a force over a force. So you would have newtons over newtons, and they would cancel. So when you actually look up numbers for mu for different situations, they are just pure numbers. And what it really is it describes how rough two surfaces are. So you probably already intuitively know this, you just weren't really aware of it yet. Different surfaces have different roughnesses to it. So if you were dragging a wooden crate across ice with a certain amount of force, you'd get very little friction. If you were dragging that same wooden crate across sandpaper or asphalt or grass, then you would have different coefficients of friction. You have different amounts of friction because all of those surfaces are different, so they're going to give you different amounts of friction. There are two kinds of friction. There is static friction, and then there's sliding friction. And it appears that I have misspelled sliding, so there are not two N's in the word sliding, there's only one. But anyway, if you are pushing on, let's say, a really heavy table in the classroom, but you're not pushing hard enough and it's not moving, then that's static friction. So the reason why it is not moving is because there is enough friction to oppose however hard you're pushing. If you push hard enough, though, you can get it to slide, and there's a different amount of friction there. So we have friction where things are not moving, and there are still forces being acted on, and then there's sliding friction, where there's still something trying to oppose you, but you overcame it enough, and you got the object to move. Another word for sliding friction is called kinetic. But just to show you the two differences here, static and sliding / kinetic. So that means we've got two different kinds of coefficients of friction. So for the same two materials, let's say we've got the box and the floor. So cardboard across a wooden floor. It has one coefficient of friction where it is static, and then it has a different coefficient of friction where it is sliding across the floor. So mu s is the coefficient of static friction, mu k is the coefficient of kinetic / sliding friction. In other words, it's moving. So one of them is not moving, one of them is moving. Let's do an example where we can actually calculate it. I'm pulling on a box, and this box is sitting on the floor, but it is not moving, so we will say it's at rest. And if it is not moving, then that means all the forces are balanced. Okay? If I said that it had 7 kilograms, and I was pulling with 50 newtons, and yet it was still not moving, then we already know all the forces. So pulling to the right is 50 newtons, there has to be 50 newtons of friction, and if it weighs, if it has a mass of 7 kilograms, then it weighs 70 newtons. And then that means our normal force, since we're on a flat surface, is also 70 newtons. And my question for this example is, how do we find out what the coefficient of friction is? Well, if we look back at our equation, all we have to do is find the frictional force, and we have to find the normal force. And that's super easy, because we already have it in our diagram. So I'm going to solve that for mu, and then we just plug in our numbers for friction and normal force, which was 50 and 70 newtons. Divide those out, and that's our coefficient of friction. So if you notice, we had 50 newtons divided by 70 newtons. That means there are no units left. So our answer is just a pure number, 0.71. Let's do another example. Let's do one where the thing is actually moving. And so that we can practice using our F net equals ma equation, let's say not only is it moving, but it is also accelerating. And here are the values I give you. It has a mass of 5 kilograms. I'm pulling with 12 newtons of force, and we're pulling it across a flat surface. And we're pulling hard enough to where we can make it accelerate. So it's getting faster and faster. My questions are, what is the amount of friction involved, and what is that coefficient of friction while it is sliding? Alright, so we need to start using both equations now. For this example, I put in this little k right here to indicate that we're talking about kinetic coefficient of friction, because the box is moving and accelerating. But first we want to start here. We need to find out what friction is first, so we can plug it in to that equation. So I'm going to write out what my net forces are, and if we look back to the picture here, we've got all of our net force is going to point to the right. So we're accelerating to the right because I'm pulling harder than friction is pulling. So I'm going to have to redo this. Okay, so let's solve for friction using F net, M, and A. So our net force is the force of my pull. F was what I gave you. And then friction we don't know. But we know everything else in that equation. We know the mass, we know acceleration, we know the amount of pull. So I can plug everything in and solve it for the frictional force. So I'm going to do one more step and simplify. 12 newtons minus friction equals 10 newtons. And when you solve that for friction, you're going to get 2 newtons. So there's only 2 newtons of force for friction, and there's 12 newtons of pull. Alright, so our net force here is 10 newtons. But we are not really interested in net force, particularly for this one, but in case you're curious, that's what it is. 12 minus 10, and that'll give us 2. Oh no, excuse me, 12 minus 2, and that'll give us 10. Alright, so our next step is to find out what the coefficient of friction is by using the friction we just calculated. So 2 newtons, we're going to plug it into this equation here. So the coefficient of friction is going to be the frictional force divided by the normal, and we plug in our 2. Our normal force in this case, since we have no motion vertically and it's on a flat surface, we know that the normal force is equal to the object's weight. So we plug this in, calculate it, and then there is our coefficient of friction. So we got 0.04. Alright. So there is another way you can find the coefficient of friction, and you can do this experimentally. And this is actually what you will be doing in class soon. So if we can measure somehow the frictional force, and we can somehow measure the normal force, and we were able to change one of them and see how the other one is affected, we could graph it, and then whatever comes out would be our coefficient of friction. Because we said that this is a constant, That right there is a constant. So that means our graph here is just going to be a linear slope, like this. And so our slope of that graph here is going to be that coefficient of friction. So you can design an experiment where if you could figure out how to change this or calculate this, find a way to manipulate that variable and see how it affects the frictional force, then we plot it, and then we get our slope, and we found the coefficient of friction. Okay, that is all for this little set of notes, all about friction, coefficient of friction, how to calculate it, and how to use it in sample word problems. All right, I will see you guys in class.